All right. Let's see if this works now. Ooh, bigger screen. All right. So what we're going to do is we're going to call each one like Z0, Z1, Z2 to represent all to the 0 power. So Z0 or 1 plus I to the 0 power rectangular form was just 1. How would I graph that? On the x-axis. Yep. Good. So here is 1. Change colors. So here we go. This will be called Z0. This is our starting point. And then we have Z1, which is 1 plus I. How do I graph that? Good. So it'll be right 1, up 1, right? So it'll be like right here. We'll call this Z1. We all agree? Z2 would be? Okay. So this would be like 2I. So Z2. Z3? Very good. Z4? X. A real number is going to be on the x-axis. Imaginary. There we go. And I asked if you would put it as a vector so you could kind of see it. So here's the first vector. Here's the next vector. So what the vectors here will do for us is to make sure, what did we find out we were doing each time in our degree of rotation? We were going by 45. So if my vector is halfway through quadrant 1, does that look like it would be about 45 degrees? And then if I'm on the y-axis, does that look like it was another 45 degrees? And then if I'm halfway through the second quadrant, does that look like another 45 degrees? And then being on the left side of the x-axis, that look like another 45 degrees. So that first theory of our degree of rotation being added 45 degrees, geometrically, looks like it's panning out. The next thing we saw is it had a dilation of a scale factor of what? Square root 2 is approximately like 1.43 or something like that, right? So it's like 1.5 times. But regardless of what the actual limit is, does the vector look like it's getting a little bit longer each time? Right. So we definitely know there's a scale factor. Might not be able to easily identify that's the square root of 2, but we can definitely tell that's getting longer and longer each time. So it looks like geometrically, it looks like it's working out for us. I'm going to keep this graph up and then answer the questions below it. The next one says on 5, predict what the modulus and argument will be for 1 plus I to the 5th power would be without actually performing the multiplication. So go ahead and do that now. Just think about what would the modulus and argument be without actually doing 1 plus I times 1 plus I times 1 plus I 5 times. We'll see if we can come up with the answer. That's an R. Oh, N on the notes, what's the degree? Whatever degree is given. Like for this one, the degree here would be, the N would be 5 because this is 1 plus I to the 5th power. So the N in this case would be 5. Birthday or just congratulations? You're welcome. Oh, well, you're the only one in this class. So congratulations. Specifically, just you. We all got a roundabout answer. All right, what do we think the modulus would be? Okay, 4 and square root of 2. Can you tell me why? Very good. So you're basically knowing that we need to multiply by the square root of 2 each time. So if the last one was 4, 4 times square root of 2 must be 4 square root of 2. Love that assumption. Now, let's say we didn't do that chart. Would you then go through and figure out what each one is until you got to the fifth one? No, that seems to be a lot of work. So what we can do is let's see if our formula works with that assumption. Our formula from yesterday was the r raised to the nth power, right? So the r would be the modulus, n would be whatever degree this is. So in our case, we want to know, does the square root of 2, that's what we calculated as our modulus yesterday, raised to the fifth power would in fact give me 4 square root of 2. All right, so let's think about that a little bit. Square root of 2 squared would be what? Just 2, right? And if that square is there twice, 2 times 2 would be what? 4. So let me kind of argue it this way. We can argue that this is the same thing as the square root of 2 squared times the square root of 2 squared times the square root of 2. Would you agree that it's the same thing as the square root of 2 to the fifth? Then you would then also argue that the square root and the square would do what? Cancel each other out. So this ends up being 2 times 2, which is 4, and then I have this lonely square root of 2 left. Right? Of 1 plus I to the fifth. One thing to note as well, what you could always do is just take the even version, the next one down, and then just apply that one and then bring that modulus back in. But then that doesn't always work out because sometimes you can have a coefficient and a radical going on. So there's a little bit of math going on. All right, but regardless, that's a lot easier still than doing 1 plus I times 1 plus I times 1 plus I, getting the complex number, and then taking that and doing the square root of a squared plus b squared just to figure out that the answer was 4 squared root of 2. We agree? All right, so if we have a chart, we're doing all of them, sweet. You can take the previous one, multiply by the square root of 2, we got our answer. But if we have to start at 5 and we don't have a chart, we can also go by this process as well. What did you say the argument was then? Okay, 225 degrees. And how'd you get that? Added 45 to the previous one. The previous one was 180. So 180 plus 45 should be 225. All right, let's test that theory. Our formula that we calculate for our argument was n times theta, right? Or theta times n or something like that from yesterday. Okay. So if the formula was n times theta, that would just be 5 times 45 degrees. 45 degrees would be that theta for the original 1 plus I that we calculated. And if you plug this into the calculator, what is 5 times 45 degrees? 225 degrees. So we see that our formula does in fact work out, or if we just add it and multiply the previous thing. We good with yesterday? All right, part 6 then says, all right, if this is what you got, let's go ahead and graph it to again verify what this would be. So I don't have a rectangular form right now. I'm going to show you that next. Halfway. Okay. So if I went halfway through, I know I would need to be somewhere about right here. And then I know it needs to be somewhat of an extension. So I'm going to go about right here, give or take. I think Z5 is right here. But here's the issue. We can't just approximate. We need to know exactly how to find this answer, right? So we'll pause there on that part of the graph. And let's talk about 7, and we'll bounce back to this idea. Does everyone have this written down at least? Have this little drawing. We'll figure out what that exact coordinate is here in a second. We all good? I'm going to erase. I'm not used to such a big pad. This is nice. So let's look at 7. So now what we're going to do is we calculate what all the rectangular forms for every single one of these are, but now we want to put it in polar form. Now, what's nice about this is you know what the modulus and the argument is from that chart. So we can kind of fill out what our polar form would be. So in 1 plus I to the 0, what was the modulus? 1. And then that becomes cosine of, what was the argument? On that one, it was either, okay, gotcha, but it was 2 pi or 0, right? Let's start with 0 for the sake of argument. Would you argue that that would be the polar form, right? We have the argument and we have our modulus. You don't necessarily have to write the 1 there because, again, 1 times anything would be itself. So now let's go through this next part right here. What would this one be? What would be the modulus of 1 plus I to the first power? What was it? Not just 2. It was square rooted. Wasn't it square root of 2? Yeah, just square root of 2. Cosine, what was the argument? 45 degrees. If you haven't already figured out the pattern, go ahead and finish it all the way down to the 4th power, and then we'll catch up there. Yes. Yes. Well, do you want to wait until the crowd goes down? Hannah, can you tell me when you told her that? Was that today? Was that today that you told her about the good hearing? Maybe we were just too busy yesterday. I haven't heard about it yet. Just trying to figure out how busy I need to be outside before coming in. Yeah, with the sun out. He's like, no, hold up now. What we talk about in pre-cal, we don't have to discuss in Miss Smith's class. I will say though, if I get in trouble, I'll just start taking grades. No, it did not work out in my favor there. All right, we ready? All right, so the next one would have been just very good. Very good. Was that 135? And then 4 was the last one? All right, so there we go. So we now turned every single one of those into polar form. Number 8 then says, use this pattern now to turn what we just did in number 6 into also polar form. So on number 8, how would I write 1 plus I to the 5th power in polar form? Perfect. Any questions on that part? Now, on that one, it then says convert that into rectangular form. I can easily convert this guy into rectangular form versus having to do 1 plus I times itself 5 times. What is cosine of 225? All right, I'm going to do this. Just know this goes for number 8. I'm just running out of room there. That's perfect. And then don't forget the I. Now, what would I do next off of yesterday's opening exercise? Distribute. Very good. And hopefully we're getting a little bit better at multiplying with radicals. What is 4 square root of 2 times negative square root of 2? 225, yeah, is that what we did not catch? Number 7? 225, negative, negative. 225.
All right, so I'm wrong. That's not. Can you remind me to change this?
No, it's right there.
Yeah, it's 210.
No, that's 210. That's your 225. That's your 240. I don't know. There you go. Okay, so again, so what was 4 square root of 2 times negative square root of 2? Okay, it starts off at negative 4. Okay, I like that. Square root of 2 squared over just 2. Good. The denominator is not going to change. And then we can see this is going to be the exact same thing over here. Now, what do we know is going to happen to that square root and that square? They cancel. An alternative way that you might have done that is you might have said that's the square root of 4. But regardless, what's the square root of 4? 2 as well. So regardless of which direction you went, you would eventually got to this times 2. But do realize that this needs to then be multiplied here. So what is negative 4 times 2? All right. Now, I guess let me pause there. Do I have to multiply this? What could I do instead? I could cancel because I'm multiplying by 2 and I'm dividing by 2 to save myself some time. I can just cancel those out. And now I have negative 4 minus 4i. Go ahead. Did you end up doing 4 times 2 to get the 8? That's fine. Mm-hmm. Exactly. As long as you reduce it down to at least 4. Perfect. Any other questions there? However method you do it, as long as you're getting to this method, there's quite a bit of different directions you can go with those square roots. Now we actually have a coordinate. So if I was to bounce back to that graph, oh man, I wish it would have saved the stuff. That'd have been great. But y'all have the graph, right? Okay. So I'm just going to graph the Z5. I now know exactly where that coordinate's going to be. It's going to be left 4 and then down 4. So I know I'm going to be exactly right there. So now I know where that Z5 is going to be. So I know I'll no longer go, well, I know it's going to be halfway through because it's a 45 increase, but now I know exactly where that coordinate would be. All right, so you go back and edit that now. So you know the marker there. Is there any questions there? All right. So now, come on now. There you go. All right, so let's look at number 9. So I could do the chart and find out what 1 plus I to the 6th, 1 plus I to the 7th, 1 plus I to the 8th, but I think I'd be here, Raul, just still multiplying by the square root of 2 or adding 45 that many times. So here, what I want to do is I want to figure out what the polar form is of this guy right here. And to start off, it says find the modulus. So if you recall, to find the modulus is going to be the original modulus to the nth power. Okay. So what was the original modulus of 1 plus I? Square root of 2. Correct. That would be a 1 plus I to the 0 power. You're going to want to pay attention to the R of the 1 plus I to the 1 power. Yeah, because all of those would technically all be the same if we did the 0. But this will be the square root of 2 to the 20th power, right? So I don't know if y'all solved this in Algebra 2, but I'm going to show you a technique here. The square root, does anyone know if that's written as a rational exponent? Does anyone know what rational means? So a rational function is a fraction. So I want to turn this radical square root of 2 into a fraction exponent. Basically, it's what a rational expression would be. So I'm going to turn the square root of 2 into 2 in 1/2. Does everyone understand where the 1/2 came from? Gotcha. In radicals, you were supposed to, I think it's actually over there. But radicals are written like this, where this right here, this I represents the index, and this E represents the exponent. So I can rewrite this as exponent over index, also known as E over I. So you're like, well, I don't see a 1 or a 2. How'd you get those things? Exponents with no power has an imaginary what there? 1. If this radical doesn't have an index showing, we usually call this the square root. Square is usually typically correlated to what number? 2. All right. So when the index is not written, a square root has an imaginary 2. So that is where the 1 over 2 comes from. Now, you might be asking the next question, why in the world are we trying to turn these into fractions? Well, if I now have 2 to the 1/2 raised to the 20th, what's my exponent rules tell me when I have a power raised to a power? What do I do? Oh, there's 3 main rules in exponents that you're supposed to learn in Algebra 1. When you are multiplying like basis, you want to add their exponents. When you are dividing like basis, you subtract the exponents. And then a power to a power, you're going to multiply them. Tough? Yeah. It is, as long as it's just a square root. If there's like an exponent or an index, you'll be dealing with something differently. But for this sake of what we're this topic, it's typically always going to be the square root of something. Right? So therefore, a power raised to a power, I need to multiply these things. What is 1/2 times 20? Just 10, right? Basically, when you're multiplying by a fraction, you're asking yourself, what is that fraction of? So what's half of 20? So now I really just have 2 to the 10th power, which is something a lot easier to do. You can obviously type it in your calculator, or you can try to work it out in your hands. So let's see if we can do it with our hands before, and we can verify with the calculator. So 2 times 2 would be? There it is. You ever played that game? 2024 or whatever? Or what is it? The 2048, I think so. So is it 1024? Is that what we got? You never play that little sliding game with the boxes and the numbers? 2048 is what it's called. It's not. It's the only game I can play with no internet, and that's what I typically play in the deer stand because I have no internet. I'm like, oh yeah. All right, but 1024 would be the answer. So that would be the modulus. Of course, you have a calculator. So if any of this was confusing, you could just always just do the square root of 2 raised to the 20th power and just call it a day. But again, as your math teacher, I do want you to understand the math behind it. But as long as you're getting the 1024 or whatever the correct modulus is, I'm good there. I did not finish spelling this out, but this was modulus. I don't know why it stopped. Now to find the argument, remember our formula was n times the original argument. In this case, what was my original argument? 45. Good. So I need to do 20 times 45. What is 20 times 45? 900 even? Well, technically 45 times 2 is 90, then add the 0 at the end. Now you get 900. Yeah. So now to write this in, so we now found the modulus, we found the argument. So now we're able to write this in polar form. So when we do this in polar form, that's going to be how? How do I write this? Very good. Good. So there's our answer. However, it gives us one last question. It says, explain why this is a real number. Well, the only way to do that is to do the work. So I need to work this out to figure out what this rectangular form is. But you might be asking yourself, we only go to 360. What's 900? What do we know about circles? They keep going. So here's my best advice to you. If you have something larger or less than 0, or larger than 360, just subtract 360 until you get a number between 0 and 360. So what's 900 minus 360? It is something. Not quite. Not 720. 540. All right. 540 is still not between. All right. So 540 still is not between 0 and 360. So let's subtract 360 again. What's 540 minus 360? Yes. All right. So therefore 180 would fall here. So there's your coordinate for 900. All right. Because remember, a circle just keeps on repeating the same pattern over and over again. Your objective is just to get it down between that 0 and 360 so you can kind of figure out where you're at. So cosine of 900 and sine of 900 will correlate with -1 and 0. So let's do that. So we now get 1024. And then this would be -1 plus 0i. But what's going to happen to that 0i? Just stops existing. And then what's 1024 times -1? So there's your why this ends up being a real number. So you don't have to actually do it in words. Math itself can prove that. Any questions there? Go ahead. That's when you subtract exponents. Numerator by denominator. But my rule of thumb when I teach it is I just tell them to find the difference of the two, and whichever exponent is larger, that's where the result will go. Because a lot of students don't remember what the rule is when they get a negative exponent. Because if you get a negative, so let's say you have x squared divided by x cubed, right? You're like, oh, I remember to subtract that. So that's 2 minus 3, but that's -1. So you're like, all right, the answer must be x to the -1, but that is not technically something we do in math. So we rewrite that as 1 over x to the 1 power, or just 1 over x. So I tell students just find the difference of 3 and 2, which is still just 1, but then put the answer where the larger one is, so it goes right back to the denominator. All right, so that was number 9. So let's look at 10 through 12 to kind of recap all this and put a little bow of a formula to this. So on number 10, it says, if z has a modulus of r and an argument of theta, what are the modulus and argument for z squared? Write the z squared and polar form. So to write this in polar form, what would my r or my modulus be of z squared if I don't even know what z is? How would I figure it out? That's it. It's just going to be whatever the r to z is squared. So that's what the exponent is, times the cosine of what is my angle going to be? Very good. I'm going to write it as 2 times theta. So I don't need to know what theta is. I just need to multiply it by 2 and then plug it in for each one. You'll all agree with this statement? So if you agree with this statement, how can we write a formula for every single answer to any n power? Very good. So you now have a formula. So if you're given a theta, you just got to go, or a complex number, you just got to go find its modulus, go find its argument, and then plug it into this equation corresponding to whatever nth power you're looking for. So if you reflect back on that unit test or the mid-unit test that we just took, z to the 4th now becomes a way easier problem. And I wish they would have shown this before giving that as a thing rather than trying to give that to you beforehand. Any questions there? One little last part here. When talking about dividing, is this going to be the same concept? If it's 1 over z, this is going to be 1 over r. And then remember to find its theta, we take 360 minus the theta. All right. So this can be the same concept as this. So 1 z to the n. So if you're basically what this means is if you're asked to find 1 over 1 plus I to the 4th power, It's going to be the same process. It's just the first part of your modulus is going to be its reciprocal. So that'd be 1 r to the nth power, or in that case, to the fourth. And then this would be cosine negative n theta plus I sine negative n theta. Right? So if you are dividing, that would be your last formula. And that does wrap it up a little bit. I was going to give you a couple examples to try, but due to technology, we ran out of time. Enjoy y'all's weekend, guys. If you are doing some parties or something for Halloween, be safe. Don't drink and drive. Get a designate. That is correct. Make sure you're being safe, guys.